This is part 4 of talk on the Standard Model leading up to the mathematical Yang-Mills millennium problem. And I'm using a different encoder for this part of the video because the other one was being extremely slow in uploading. Hopefully this will look more or less equally good. So I want to talk about electricity, magnetism, and light. So it's definitely a particular topic in physics, and it's going to be of particular relevance to this story. All three of those things seemed quite separate at first. Electricity, when they first discovered electrical phenomena like static electricity, things like that, and magnetism seemed quite separate. But fairly soon, fairly early on, people discovered that they influenced each other and therefore must be linked in some way. And light seemed to be a completely different thing. They were all unified gradually in the 19th century, and Maxwell is the name usually mentioned as the person who really synthesized it all, and in particular crowned the whole achievement of many people by realizing that, yes, you can combine electricity and magnetism. You get a very precise mathematical theory, and out of that mathematical theory pops a prediction that light will be actually an electromagnetic wave. It's just a stunning prediction. And one of the things that the mathematical techniques that's going on here is the idea of a field or force field. And let me say a little bit about that. So here's some pictures. Here, if you have a positive charge and a negative charge, these lines, these black lines, let's ignore the dotted lines, that's something different. If you look at the black lines and arrows, that's the field of these charges. And what that means is if you are another positive charge right at this point, then you will be pushed away from that positive charge and also towards the negative charge, and the effect of that is you're going to be pushed along one of these lines. And what that does is it gives a formalism that answers one of Newton's objections to his own theory, his theory of gravitation, that he was disturbed by, which was action at a distance. That how does this positive charge act on something, say, that's out here without touching it? Now, I'd say mainly you could just say, look, that's the theory. From now on, things don't have to touch each other to influence each other. But it turns out that he was rather prescient in having that as an objection. It only when you get to things like relativity and Einstein does that become a really fundamental objection in some way. But what you posit is that this positive charge creates a field, something not something that's matter, not something that's stuff necessarily, but at least you could just think of it as a mathematical description, that at every point in space it tells a point, some other charge there, how to be pushed around. Similarly, magnetism can be described as a field that does something to where everything in space. And here it's an actual physical picture of iron filings around a magnet, and it turns out that those filings actually line up in a way that gives you a physical picture of this force field. What you can see very dramatically is that at every point in the space around this magnet, any little iron filing at that point will be affected in some way. In this case, they're caused to orient parallel to the lines of the magnetic field. So it's a beautiful, beautiful achievement, but there's a huge problem. That the theory, Maxwell's theory, and in particular the predictions about light, seem to violate a fairly reasonable principle, one that people thought was pretty important, and that was Galilean relativity. The idea that if you did an experiment, it didn't matter whether you were moving or in what direction you were moving or how fast. And so pretty much everybody said, or most people said, well, I guess the symmetry isn't really real. Maxwell's theory is so good, it's so unavoidable, its predictions, we're going to ditch the symmetry and we're going to introduce something called the luminiferous ether. And that is some substance that is the mechanism, the stuff, the mystery stuff that the electricity and magnetism is propagating in. And so, for example, if the Earth's going around the sun, you should actually get different answers for certain experiments, but especially experiments about light, if the Earth is going one way or going the other way through this ether, so that its motion relative to the background of the ether should be detectable. Well, experiments proved that that wasn't true, that it was looking like Galilean relativity seemed to still work, except they knew it was incompatible with electromagnetism. Einstein was brilliant in that he was able to save both theories, both principles. He just had to reinterpret Galilean relativity. It wasn't exactly the equations for Galilean relativity, the particular naive mixture of space and time that you can think of as encoded in that version of relativity. was not true. But there still was a relativity principle that you really couldn't tell physically which way we were going, even if you did experiments with light. And so he basically reinterpreted symmetry to fit the electromagnetic laws of Maxwell, and they fit beautifully, and it leads directly to special relativity. And so symmetry is saved as a principle in the process. Now, Maxwell's electrodynamics, it also has a local symmetry. It has a certain kind of thing where you can adjust it locally and differently for all different parts of space. And initially, it was unclear what that was a symmetry of. Nowadays, and this really is kind of post-states, this kind of comes after kind of quantum mechanics comes in, but nowadays what we could imagine is that particles are really sort of everywhere in the universe has a little clock attached to it. And these clocks whiz around really, really super fast. And it turns out that it's easy to show that you could reset everybody's clock simultaneously in the same amount, like set everything ahead 1 hour, and it wouldn't change the theory. But in fact, there's a way to reset everybody's clock differently, like the time zones. This is called gauge symmetry or local symmetry. And you can ask everybody to reset those little clocks differently. And if you set up the mathematics right, you will still get the same physical predictions. And so it's very much like the idea of the ability for everybody to change their clocks differently, as long as everybody talks to each other and has a system for figuring out how those relate to each other. So there's two huge consequences of local symmetry that I alluded to in the case of relativity. One is that Noether's theorem comes in and says, okay, if you've got a local symmetry, turns out there's always a conserved current associated with that. Guess what? That's electrical current. It's another reason. It's not the only derivation. It's not the original derivation, but it's a cool post facto derivation that there's this stuff called electrical current, and it can't be created or destroyed, but it can move around. And so, for example, a dramatic illustration of that is lightning. This is that volcano in Chile a few weeks ago. And as in relativity, this is even harder to put over precisely than the Noether's theorem thing. But as in relativity, whenever you've got this idea of a local symmetry, the mathematical construct that's necessary to relate everybody's data to each other so they can still talk to each other turns out to have exactly the requirements that make it look like a force field. And so automatically you get electric and magnetic forces from this local symmetry. So it's astonishing, really. These two principles give everybody a clock, or should really give every point in space a little clock that whizzes around, and then just let them adjust them independently. Automatically gives you, in this very broad general framework, automatically gives you electromagnetic forces, light, and a conserved electric current. It's just awesome. Or another way to say it, or one aspect of it, is suppose we know from experiments, as we do, that electric charge is conserved. If you put in charge into, or put some sort of amount of charge into something, it doesn't just disappear. It can spread itself out, it can accumulate, it can move around, but it can't just be destroyed. And so that suggests strongly that electromagnetism ought to come from a local symmetry principle. Even if we didn't know already from the equations that they had this adjustability to them, we could have predicted it from that conserved current. Or at least it would have been very suggestive. That's not how things happened historically, but for other theories, it's closer to what happened historically. So far, what's the story here? Electromagnetism and light have been unified. Gravity is ruled by a similar idea, and it wasn't until later that people saw exactly how similar it was. Symmetry, various kinds of symmetry principles are fundamental to both theories, although again, it was only later that people kind of realized how fundamental they were and elevated their importance. Some of that symmetry is external symmetry, these space-time symmetries, like moving things around. You can actually see it happen. If I actually move my lab from here to Santa Fe, then it's very visible what I'm doing. Some symmetry is internal, much more harder to see, and it usually just comes out in the mathematics of the theory, that you've got these formal, like little clocks that are associated to every point in space-time. What do those clocks measure? They don't measure time necessarily. They don't measure space. They're just some additional property of things in the universe that we can mess with. And the fact that we can mess with it and it doesn't change the theory turns out to be incredibly important. So far, though, in my description, it's all classical and not quantum. And a couple other things is that particles, the stuff, the matter of the universe, and fields like electric and magnetic fields are quite separate from each other. And fields do things to particles, and particles create fields. Well, why not? What's wrong with that? Well, we'll see that those are actually going to unify, surprisingly, as well. And then fields exhibit wave behavior. The waves supported by electromagnetic fields, for example, that's light and other kinds of like radio waves. And they carry forces. And that seems very different from what matter does. Matter just sits around and reacts to the forces or creates the fields, but they seem very different. So now here comes quantum mechanics. The quantum revolution, 1900 to 1930. Particles sometimes behave like waves and vice versa. Waves sometimes behave like particles. For example, electromagnetic waves, people were pretty sure that light was an electromagnetic wave, and suddenly it's behaving in some situations like a particle. Another thing about quantum mechanics, which I'm not going to focus on, but I have to mention, is it's a probabilistic description of the universe. It does not make explicit predictions. It is not deterministic. It's fundamentally probabilistic, as far as anyone knows. There's theorems to the effect that say it's almost certainly probabilistic at a very fundamental level. And it is fundamentally counterintuitive. It is really hard to get used to the ideas of quantum mechanics. We won't need to understand much of those counterintuitive ideas for this talk. But originally it still had particles/waves, the stuff, the matter in the universe, and fields, which were the things that had forces. They kept them separate. It's sort of your typical undergraduate quantum mechanics problem says, here's a potential, which is essentially the data of a force field. What does it do to the particle or the wave? Okay, and it was still not unified with special relativity, but people knew very early on that that was something you're going to have to do. So sort of in parallel with the final development of non-relativistic quantum theory, quantum field theory started being developed, and that was the relativistic version. And the immediate predictions of that, or pretty quick predictions of that, were that everything sometimes behaves like a particle. Everything, even fields, even force fields. Everything obeys the laws of quantum mechanics, including the force field. In fact, everything is a field behaving like a particle. And that's an incredibly important thing. That's everything you can imagine, everything in the universe, including you, all the pieces of you, that's a field behaving like a particle. Now I'm going to explain a little bit about what that means. And in particular, the whole thing about the quantum mechanics is that the appearance of unexpected discreteness everywhere. That was the original reason for the word quantum, that things that we thought would come in continuous packages that of any size that we wanted came in discrete quantum lumps. And it just shows up everywhere. So an example of that, one of the favorite, let me do the animation here. One of the favorite examples of that that people like to talk about, which gives you a feel for the idea. It's not exactly what happens with quantum fields, is standing waves. If I have a string oscillating and the ends of the string are fixed, like somebody's holding that there and holding that there, and those are not moving, and then I let the string oscillate in a wave motion. That's called a standing wave. It's not traveling left or right. There's only a few ways it can do that. It could have exactly one half of a cycle, or one full cycle, up, then down, then back, or 3 half cycles, or 4 half cycles. Notice up, down, that's really 2 full cycles, or 4 half cycles. It can have only an integral number, a whole number of half cycles in there. And so we've got something that's fundamentally continuous. It's the motion of this string, which essentially has sort of an infinite number of little bits to it, or a huge number anyway. It's essentially something that varies continuously, and yet because of a condition, the fact that the endpoints are fixed, we see that it can only oscillate in really a discrete number of ways. And maybe it can oscillate in a combination of these. It'll maybe have a sum of different components put together, but the building blocks are discrete. And that's very, very roughly what happens in quantum field theory, is that you've got these fields that are in every point in space, and that it could sort of theoretically have any value, and yet the oscillations that they actually end up being allowed to have are just a discrete set of oscillations in most cases. So the standing wave, for example, back to that example, if you have a guitar, the reason a certain string on a guitar has a certain note is that it can't oscillate in whatever way it wants to. It has to oscillate in some combination of those fundamental standing wave modes that I showed you in the previous slide. Those combinations can combine in a somewhat complicated way to create waveforms like this instead. But it can't, the E string on the guitar has to have as its fundamental oscillation the E note, and it's going to have some overtones as well, but it's not going to suddenly become E sharp just because it feels like it. So that's this unexpected discreteness that sometimes happens even in a continuous system. So let me focus on different descriptions of light to give a picture of this sort of the historical process. Again, my talks are never historically accurate. It's always kind of an idealized version of what should have happened, especially if everybody was thinking like a mathematician. But here's some different descriptions of light. Newton said light is a particle. He had very good reasons for believing that. But after Newton, everybody else was convinced that light was a wave. There was too many good reasons for believing it must be a wave. But a wave in what? What's the stuff that's oscillating? Well, Maxwell said, he identified what it was, essentially. Well, light is a wave-like oscillation of electromagnetic fields. And that seemed like absolutely the right answer. But then Einstein comes along, and in a totally different insight from his relativistic insights, and the thing that really won him the Nobel Prize, or one of the things that won him the Nobel Prize, was that he analyzed what's called the photoelectric effect. And he said, well, yes, I believe, Maxwell, that light is a wave-like oscillation of electromagnetic fields. That seems continuous. But when it interacts with matter, it's acting like a particle. We can't avoid that. The data is clear, and here's the only explanation for it. It is acting like a particle. Let's call it a photon. And then I put a big huh there, because that just doesn't seem to make any sense. When is it a particle? When is it a field? Which is it? Is it both? Is it neither? Is it a weird mixture? Quantum field theory comes in eventually, in about 1930-ish, to say, we can explain this. Yes, fields are important, but the way fields work, because of quantum mechanics, they're unavoidably quantized, somewhat like that standing wave example, so that only particular excitations of the field are allowed. So a photon is a particular kind of oscillation of the quantized electromagnetic field. Not all oscillations are allowed. They come in discrete sets, and that makes it act like a particle. This isn't the final word on it, but that's sort of a basic quantum field theory description. Is that you can imagine that there's this photon, there's this electromagnetic field, and it looks like a string, and it can be buzzing and oscillating, but it can't oscillate in any old way it wants to. In many situations, it is discrete, and it ends up acting like a particle. Conversely, again, sort of this unification, we're seeing that the discrete and the continuous are being unified in an unexpected way. That continuous phenomena turn out to be discrete. Well, discrete phenomena, particles, can actually be used to explain these fields. You can actually explain any kind of field behavior in quantum field theory by introducing lots and lots and lots of particles. And in particular, one way this happens is that you look at the description of forces. It becomes rather different in this picture. We get what's called Feynman diagrams, with particles whizzing around. And this particle, for example, what's going on here, time is going from left to right in this picture. That's what the T is for. What's happening is an electron and a positron, a positively charged anti-electron, come together, annihilate, create a photon, and then that spontaneously creates a quark and an antiquark, and then that antiquark spits a gluon out. It's not incredibly important to know what all the different particles mean at this point. It's just the idea that we have particles, and we have particles interacting, and we have these formal diagrams of things going in straight lines and interacting at what are called vertices, places where these lines intersect. The wavy line is the standard thing for a photon, and this curly line is standard thing for what's called a gluon, which is going to talk about the strong nuclear force eventually. And here's another picture. In this picture, let's say time is going from the bottom up. I probably should have reversed one of these or rotated one of these. Let's say time is going from the bottom up. This is something where you could imagine two electrons are getting near each other. And when electrons get near each other, they're supposed to repel, so they should end up kind of going away from each other. Well, one explanation of that is one way that can happen is that they exchange a photon. And one of the amazing things that Feynman observed is that as they do that, the photon just on a whim in the middle of the process could spontaneously become an electron-positron pair and then kind of re-annihilate and become a photon again. And so as these electrons are interacting, they're interacting by throwing a photon back and forth, and then those photons get some extra funky contributions to the equations based on the fact that they can kind of turn into electrons and positrons. It gets very complicated, but it turns out that these diagrams were the big key to how to calculate all this stuff. I'll talk about that pretty soon. This is a good place to stop this part, though.